Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fazil Faisal bin Abdul Rashid. I'm from Department of Industrial Engineering, College of Engineering, University Malaysia, Pahang. So for today, I'm going to present my paper with title Development of a Discrete Event Simulation Tool for Assembly Line Simulation. As an introduction, discrete event simulation or DES is an approach that used to mimic an actual system as a series of events. Okay? So the purpose of DES is to research the system behavior. And discrete event simulation has been used in lots of applications such as in production, logistics, services, and healthcare sectors. Okay, these are some of commercial discrete event simulation and also open source discrete event simulation. But for the commercial DES software, the main problem is the cost of the license. Okay, so the cost of the license for small and medium enterprises normally will burden them. But for open source DES, it requires good programming knowledge, and some of the software or tool is developed for specific problem. For example, for warehouse planning, okay, for the scheduling and so on. So normally they will be developed for a specific problem. So that are the problem statement or limitation of the existing software that we have. So the objective of this work is to develop a DES tool specifically for production and assembly line simulation. Right. So to achieve this objective, so we need to conduct a few activities. So we need to design the DES architecture, and we need to conduct case study in order to verify and also validate the developed tool. Then we need to simulate the case study problem using our proposed DES tool. Then we need to compare the result with actual case study problem. And we also will compare the result with a commercial DES tool in order to validate and also verify the obtained result from our simulation tool. Right, so this is the architecture of our DES tool. So the tool that we develop is called DESIMAL, which stands for Discrete Event Simulation for Assembly Line. Okay, so for the architecture, we divide into three stages: input, processing, and output. Okay, for the input, we need to define the workstation, task time, distribution type, simulation length, and so on. And then for output, we will obtain the busy time, idle time, number of output, processing time frame. Okay, so these are the output that we will obtain from the simulation. This is our current decimal prototype. Okay, we write the code in MATLAB. Right, so for the input side, okay, we need to key in the input data, which consists of the production or assembly task, the assigned workstation, okay, the processing time, and also the standard deviation. So the standard deviation is obtained from a set of the time. The time here is basically the mean of the time. Okay, so this is the input side, and this is the energy. This is basically for the future planning. All right, then we need to define the simulation length. Okay, this is the time taken. Okay, for example, we want to simulate for 8 hours, so we convert into in this example we convert into second, and in front here is warm-up period or warm-up time for the system. Right, so then we simulate
okay, how the system will perform. Right, so now we will run the simulation. Okay, so for this run, number of replication we set to 30. So the simulator will run for 30 times with different pseudo-random numbers. Okay, so this is what happened, okay, for when we run for different replication. So number of workstation, okay, the first column here is the number of workstation, then the availability of the workstation, the buffer number, then the buffer limit. So in this example we set the buffer limit is only 1, the start time, the finish time, number of operation time, and also the idle time. So every time we run, so we will obtain a different value for start, finish, operation time, and idle time, depend on our random numbers. Okay, that's why the value here is different.
Then we need to conduct a case study. Okay, case study for validation was taken from an electronics industry. Then it is consists of 23 tasks, okay, as shown in the figure, which originally assembled in 10 workstations. Then for simulation, the problem of case study is modeled and simulated in DESIMAL. Then for comparison, we compare the simulation output with commercial software. And for this purpose, we are using witness simulation software. Then the simulation parameters, okay, we simulate for 1 working days, which equivalent to 8 working hours. Then the warm-up period is 950 seconds. Then simulation is repeated 20 times with a different pseudo-random seed. Then we compare the simulation output with the actual assembly line. So this is the result that we obtain. So we measure the busy time, idle time, and number of output. So we compare between our software DESIMAL with witness, okay, for each of categories that we measure. And this is the mean of the busy, idle, and output, okay, for DESIMAL, witness, and also the actual problem. Okay, for average busy, the DESIMAL achieved 75.53%, while witness 76.69%. So the error percentage between DESIMAL and actual output is only 4.58%, and output error from the witness simulation is 6.25% compared with the actual average output. So it's indicated that the DESIMAL is more accurate, okay, to represent the actual output. And based on the reference, so if the error between simulation and actual is less than 10%, so the simulation model can be accepted. So means that in this case, both DESIMAL and witness simulation model can be accepted to represent the actual case study. Then for advantages of the proposed DESIMAL, it has good flexibility to adopt a different production line. So basically we can simulate for different type of production lines, such as multi-model, okay, U-shape, and so on. Then detailed information at assembly task level. Okay, most of simulation software only give the output information at the workstation level, but for our proposed simulation tool, okay, beside the information at workstation level, it also gives the information at task level, and it could be integrated with optimization algorithm for the assembly line. But in terms of disadvantages, it is unfriendly user interface, as I showed earlier. It required the user to have fundamental programming knowledge and limited to discrete production line application. So as a conclusion, you can conclude that this work has successfully developed and validated discrete event simulation tool for assembly line simulation. Okay, based on the result that we obtain by comparing the decimal output with commercial software and also comparing the decimal output with actual production line output. Okay, that's all from me. Thank you very much.